We have selected two presentations about two very different topics. So I hope that you enjoy our session. I will share this work together with Carlos. So maybe I can start introducing the first paper, and maybe you can introduce the second one if you agree. Okay.
Sure.
So. Okay, yeah, we have the presenter. Okay, hello. The title of the first work is wafer level package CMOS SOI MEMS thermal sensor at wide pressure range for IoT applications. The presenter is Moshe Avraham from Ariel University in Israel. I hope to pronounce well your name. So please, Moshe.
Thank you. I will share my screen. My name is Moshe, and I will present to you a wafer level package CMOS SOI MEMS thermal sensor at wide pressure range for IoT applications. Research motivation. Infrared sensors are widely used in the market for IoT applications, smart home, automotive, thermal cameras, wearable devices, and many more. Thermal sensors detect temperature changes induced by remote sensing of infrared radiation and provide uncooled infrared sensor. The MEMS technology enables to manufacture high-performance miniature and low power consumption thermal sensors. Research innovation, the TMOS. The TMOS, short for thermal MOS, is a thermally insulated transistor, operates as thermal sensor. The TMOS developed at the Technion. The TMOS is fabricated by standard CMOS SOI MEMS technology. The CMOS SOI process enables easy integration with readout circuitry. And the TMOS is the only thermal sensor that is an active device. And with applying backend machining, it becomes the highest performance thermal sensor compared to other established sensors such as the bolometer, pyroelectrics, and thermopiles. The TMOS transistor operates at subthreshold region. Therefore, it requires very low power consumption, which is very important for battery-operated devices. Here in the middle, we can see a 3D illustration of the TMOS. Here we can see the suspended transistor, thermally insulated by a very low thermal conductive holding arm. On the left, we can see an actually fabricated TMOS sensor with 2 pixels. One pixel is blind to radiation by aluminum mirror, and the other one can sense the radiation. In this configuration, the TMOS sensor can be used as a human movement detector. TMOS operation principle. How we can sense radiation and measure temperature with the TMOS. The micro machine thermally insulated transistor, which is a very low thermal mass and very low thermal conductivity, observed infrared radiation. The infrared radiation hits the suspended transistor, and the radiation hits the transistor, and the transistor which operated at subthreshold region, its voltage is very sensitive to temperature changes. So we achieve a highly sensitive sensor. In order to achieve this high sensitivity, we need to proper thermally insulate the transistor. We need to package it in deep vacuum. Therefore, a wafer level package has been developed with 3 silicon wafers. The bottom silicon wafer, MEMS and TMOS wafer, and top silicon optical window wafer. The 3 wafers are bonded together with glass-free. Glass-free is compatible with the CMOS SOI process due to its relatively low melting point of temperature. To the bottom silicon wafer, we add a getter layer. The getter reacts with the residual gas in the package and increase the vacuum level. In this process, we achieve a vacuum level of 10 to the minus 5 atmospheres. And it's stable for many years. The research question. As we say, the residual pressure of the gas determine the thermal conductance of the device, and the thermal conductance influence the thermal response time, the thermal time constant. What we want to know is what is the effect of this residual vacuum upon performance, and what pressure is critical for the proper performance of the device. In order to answer these questions, we build a model and run simulations. Let's start with the model of the package TMOS. From the power balance equation, we can say the absorbed optical power equal to the conserved power in the TMOS and to the power that leaves the device. From the steady state solution of the power balance equation, we can know the temperature differences of the device, and it's equal to the absorbed optical power over the thermal conductance of the device. The thermal conductance of the device is determined by three main mechanisms: by the solids, by the gas, and by radiation. We'll discuss each mechanism in the next slides, but it's important to note we will discuss the gas conduction and not the gas convection. We can neglect the gas convection because of the closed package and a relatively low temperature difference. The thermal capacitance of the device is governed by the TMOS stage, and it's equal to the mass density multiplied by the specific heat capacitance of the material and multiplied by the volume of the stage. The thermal time constant is defined by the thermal capacitance over the thermal conductance of the device. This problem is equivalent to a simple electric circuit with a resistor and capacitor. Thermal modeling, solid conduction, and radiation. Each body emits radiation according to its temperature by Stefan Boltzmann law. The power that body emits radiation is given us by this equation, and the thermal conductance due to this thermal radiation, it's the derivation of this power by the temperature. The thermal conduction through a solid material is derived from Fourier law and equal to the thermal conductivity of the material multiplied by the area over its length. For example, in our sensor, the TMOS, the length of the thermal conductance is governed by the holding arm. And here we can see the arm length. And if we look at the cross section of the arm, we can see the arm area. And if we know the thermal conductivity of each material of the arm, we can simply calculate the thermal conductance by the solids. Thermal modeling, gas conduction at high pressure. At high pressure for a given temperature, because of the molecules are very dense, we can say that it's like solid and the thermal conductivity equal to a constant. Why is that? Because in general, the thermal conductivity of gas is given by this formula, and it's equal to a constant multiplied by the pressure of the gas multiplied by the mean free path. The mean free path is the average distance a molecule travels before it collides with another molecule or with the device surfaces. So at high pressure, because the molecules are very dense, the distance between two molecules are very small, and the mean free path is proportional to the inverse number of molecules, and the pressure of the gas is proportional to the number of molecules. So overall, we get a constant number. For example, for air, the thermal conductivity at 300 Kelvin, it's 26 milliwatt to meter to Kelvin. At low pressure, the mean free path is governed by the device smallest typical dimension, because the distance between two gas molecules is much larger than the device typical dimension. In our device, the smallest typical dimension is the micro machined gaps. It's about 3 microns. And we see for low pressure, the thermal conductivity is linearly dependent on the pressure. The challenge is to know the thermal conductivity at intermediate pressure. At intermediate pressure, the mean free path is the parallel combine of both mechanisms. As we can see in the next slide, the thermal conductivity is given by the parallel combine of the both mechanism at high pressure and low pressure. We can see here the thermal conductivity of air as a function of the pressure. For low pressure, we can see it's linearly dependent until we reach high pressure and it becomes constant. Boundary condition. We build a 3D model of the device with ANSYS software. We assign each material its thermal properties, and we also applied the boundary condition. We assume the outer package stays at constant temperature, and also each stage of the TMOS was applied with 1 microwatt heat flow. We ran the simulation for a wide range of pressure and examined the results. Measurement and simulation results of the thermal time constant and the thermal conductance. From the steady state thermal simulation results, we can know the temperature differences of the device. And from the heat power balance equation we saw earlier, we can calculate the thermal conductance of the device because the simulation gives us the temperature differences and we know the power that we applied. We can also do a transient simulation and obtain the thermal time constant or calculate it by the thermal capacitance over the thermal conductance of the device. Because the devices are very small, there is no simple way to measure the temperature of the physical device. So the best way to measure the performance, the thermal performance of the device is by measuring the thermal time constant. We can see here on the right, in the black line, it's the thermal time constant as a function of the pressure we obtain from the measurements of the physical device. The blue line, it's the thermal time constant we obtain from the simulation. The red line, it's the thermal conductance of the device we obtained from the simulation. On the left, in the middle, we can see the steady state results of the simulation for low pressure, 2.5 Pascal, and for high pressure, 10 to the 5 Pascals, which is about 1 atmosphere. We can see the great impact of the pressure value on our measure on the signal. We can see for low pressure, we get a temperature differences of 8 degrees, and for high pressure, only 0.2. Our initial temperature was 20 degrees. We can also see there is a trade-off between the thermal time constant and the thermal conductance of the device. For a big change in the temperature differences, we want low thermal conductance, but it requires a longer thermal time constant. So for each application, we need to optimize it. For conclusions, with this modeling, the optimal pressure may be selected, and we can say the highest performance devices require residual pressure of few pascals. We also see the model simulated and measured thermal time constant are in good agreement. We want to thank Todos Technology for funding this work, and we also want to thank ST Microelectronics for fabricating and packaging these devices. Thank you for listening.
Thank you. Thank you very much for your presentation. Well, radiation sensors are very popular this year since they are the sensor element in the infrared thermometers. So they are very important. Any questions? Comments, curiosities?
Yeah, I have a question about the measurement of the pressure inside the component. How did you measure the pressure to then study the tau?
Yes, this was on another research. We refer it in our paper. it was in a capsulated package with a control vacuum. So we can measure the thermal time constant for each pressure.
Okay, thanks.
Okay. You mentioned that the stability of the sensor is 5 years, but because of the stability of the pressure inside the sensor, or is there any other reason?
And there is no outgassing. The vacuum is stable. It's no.
Okay, so
It's
the
even we have even devices that stays stable for more than 5 years.
Okay. Okay, thank you.
Thank you.
Other questions? No questions. So thanks again, Moshe, for your
Thank you.
presentation.
Good evening.
We can move to the next one.
Yeah,
Please,
we know the next one, Dr. Alexandra Makieveg from School of STEM, USA, with a presentation entitled Comprehensive Optimization of the Tripolar Concentric Ring Electrode with respect to the accuracy of Laplacian estimation based on infinitive dimensions model of the electrode. The floor is yours.
Thank you so much, sir. Let me start the sharing of the presentation. I apologize for joining a little bit late. It's still early morning here in Arizona. I made this presentation not really thinking that it will be used for a talk. So it's kind of short and I skipped a lot of details, figuring that only people who already work with concentric ring electrodes will be interested in even taking a look. So I will elaborate and expand on what is presented here a little bit. My name is Alexander Makiev. I'm an associate professor with the School of STEM here at Dana College. Here's what this talk is going to be all about. If we start with the technology itself, which I skipped completely because I figured, again, only people working with CREs will join in. Concentric ring electrodes is a reasonably novel, non-invasive wearable electrophysiological sensors that consist of multiple concentric ring recording surfaces and a central disk recording surface, hence concentric ring electrode. It started in early 2000s with Dr. Tarjan's group at the University of Miami in Florida, and then it grew like a wildfire. Every subsequent 5 years are the biggest 5 years of this technology. At this point of time, the groups that actively work with it here in the US range from Stanford and University of California in San Diego on the West Coast to University of Rhode Island on the East Coast, probably one of the biggest groups in the US. In Europe, also, there are extremely strong groups working on it, including my collaborators at Technical University of Valencia in Spain. And the reason why the technology is so popular nowadays is that concentric ring electrodes allow estimating surface Laplacian, which is the second spatial derivative of the surface potential directly at each electrode, as opposed to using a grid of regular single pole gold cup electrodes to get a much rougher estimation of the Laplacian. So the accuracy of the Laplacian estimation is paramount, hence we were trying to increase it further in the last 5 years or so. The Laplacian signal recorded instead of the actual voltage of the actual surface potential through combining signals from different recording surfaces has been used extensively to record and diagnose patients, recording from different organs and systems, from obvious candidates like brain and heart to less obvious ones like muscles and uterus and intestines. And all kinds of disorders have been diagnosed using the data from these electrodes because the advantages are the following. First of all, the second spatial derivative, the Laplacian signal, has better spatial resolution. And in case of, for example, electroencephalography, spatial resolution has been one of the issues of the technology since its inception. Second, it offers better signal-to-noise ratio, better mutual information. There is no electrode orientation problem, better elimination of global artifacts as opposed to local signal in the Laplacian. So a lot of advantages coming with that main point, that main biomedical significance of being able to estimate the Laplacian at each electrode. And in all the theoretical work on concentric ring electrodes so far, believe it or not, negligible dimensions model has been used. A negligible dimension model right here in figure 1 is basically as primitive as it looks. It's just a square grid with a point in the center. The point in the center represents the central disk of the electrodes. Those concentric rings represent the, concentric circles represent the concentric rings, and that's basically it. And since this very primitive model has been used, just because it's so simple, you can calculate the Taylor series expansion for voltage at any point, and you can combine them to calculate voltage for any circle. You can take an integral over the circle to average it out. It's very easy to work with. But because this model has been used for years, it influenced the design of actual electrodes. So the electrode at the bottom, the schematic, is the actual electrode from one of our collaborations with the Technical University of Valencia. And you can see that the rings are pretty narrow. The width of the rings is not negligible, but it's almost negligible. And the central disk is not exactly very large neither. So it's the model, the very, very basic, very easy to use model that been influencing the design. We did work with this model. I've been working with this technology for a little over a decade now, which is kind of scary to say, but it's true. What did we do with this model? We first studied the impact of increasing the number of rings, because this started with a bipolar electrode, a single ring in the central disk, tripolar electrode, 2 rings in the central disk, etc. So we increased the number of poles, the number of rings further to 3, 4, 5, 6, 7. Showed that we can increase the Laplacian accuracy with each additional ring, because in that Taylor series expansion, we can cancel out an additional truncation term with each additional ring, and canceling out the additional truncation term translates into decreasing the truncation error, which in this case is the error of Laplacian estimation. Then we realized all the models so far have been used with equal distancing between the rings. So what will happen if we change the inter-ring distances? We played with that. We realized that positioning the rings first really close to the center and then further and further and further out at increasing distances allows you also to increase the accuracy of the Laplacian signal. And last but not the least, we solved the actual inter-ring distances problem, optimization problem, which resulted in those kind of obscure optimal ranges as to where you can place each of the rings to obtain the 95th percentile, or I'm sorry, 5th percentile of the error, 95th percentile of the possible accuracy. However, the real problem is the model. It's not realistic. The radius of the central disk is not negligible. The width of the rings of concentric rings are not negligible. So we came up with a better model. And that's that finite dimensions model that we are optimizing in this particular study. So unlike negligible dimensions models, the finite dimensions model actually includes such parameters as radius of the central disk, which is not negligible anymore. It includes the width of concentric rings, which are non-negligible, which now allows us to optimize every single parameter in the electrode design at the same time. We decide on the number of rings, on the size, on inter-ring distances, the width of individual concentric rings, the radius of the central disk, which made this optimization problem finally made it somewhat comprehensive, or actually comprehensive. So the idea was the following. We have one criterion in this optimization problem, which is maximizing the accuracy of the surface Laplacian estimation. The higher the accuracy of the Laplacian estimation, the better the diagnostic yield of the resulting signal. We illustrate the solutions that we obtained for the case of tripolar concentric ring electrode, which means a central disk and two concentric rings. But as you will see, they can be extended for any higher number of rings. The principles that we were able to formulate based on the optimization result allow us to extend them to any number of rings beyond 2. These two designs in this little picture are particularly interesting because they are from our previous publications and we compared them. They are basically the best design as of year 2019, the design B on the bottom. And we showed exactly just how much we can improve on this design. The names for the designs is constant interring distances for design A, because the distances between the central disk and the first ring is exactly the same as the distance between the middle ring and the outer ring, so constant distances between the rings. The second one is the linearly increasing interring distances design, where the distance between the middle and the outer ring is twice the distance between the central disk and the middle ring. So what did we find and how exactly we ran the optimization problem? Oh, and if by any chance I hope I'm not breaking the protocol here, but if anything is kind of iffy or not super clear, any questions, comments, please feel free to jump right in, and let's turn this into as much of a discussion as theoretically possible. Everybody okay so far? Okay, right on. So this is how we solved the optimization problem. We started with establishing a comparison framework, and that's a 2019 paper with Technical University of Valencia group, Dr. Garcia Casado's group, who have been invaluable for us, extremely valuable for us. We established a comparison framework that allows you, or that is a set of steps, an algorithm that allows you to compare directly any two concentric ring electrode configurations of the same size and with the same number of rings. They can have different widths of individual rings, different radius of the central disk, different interring distances, and it shows step by step mathematically how do we compare those and how do we tie that comparison to the resulting accuracy of the Laplacian estimation. We established that comparison framework for FDM. We compared the results to similar NDM results for an actual electrode that looks like an NDM, the electrode from the very first slide with really thin concentric rings and rather small central disk. We validated our comparison framework on human electrocardiogram data. And then the question that remained was to expand that comparison from just any two designs to all the possible designs of the same size and with the same number of rings, which means we need to consider all the possible radii of the central disk. We need to consider all the possible widths of individual rings, all their possible placements, etc. So we took that framework, we developed it into an optimization problem comparing all the possible series with the same size and the same number of rings. We started with tripolar concentric ring electrode with 2 rings. We ran it for 3, 4 rings, etc. And we realized really quickly that the results are very easy to generalize, as opposed to the results of the optimization, interring distances optimization problem for the negligible dimensions model, which were all extremely mathematically intense and had to be defined in terms of optimal ranges for parameters defining the radii of rings. This one, once you introduce these additional parameters, the width of the rings and the radius of the central disk, they're actually extremely easy to generalize. We used the absolute value of the truncation term coefficients for the lowest remaining truncation term order as our criterion, because looking at even higher orders in Taylor series expansions, they can start to contribute more and more negligibly to the full sum of all the truncation terms to the truncation error. And then, of course, for each configuration, based on the number of rings, the number of truncation terms up to a certain number, equal to twice the number of rings, actually, as we have shown mathematically, is canceled out. So we are looking at the lowest non-canceled out term and its respective coefficient. We have also shown using finite element method modeling in references 2 and 3 in 2016 and 2018 that ratios of those truncation term coefficients really are wonderful predictors of the relative and maximum error of actual Laplacian estimation when we actually compared the analytic Laplacian to the Laplacian estimated through a concentric ring electrode. So we are not just using those truncation term coefficients on a whim. We have shown them to be within 5% of the respective error of Laplacian estimation. So mathematically, it's a wonderful predictor. And this is what we've seen. First, I would like to formulate the general principles that define those optimal configurations. And we're gonna illustrate those general principles on the simplest example possible. Why is the simplest example possible? Well, why not, right? We look at all the possible tripolar concentric ring electrode configurations for the outer ring equal to 6. So just think that out of the outer radius of the outer ring, we are going in increments of 1/6 of them. If we went with outer ring or outer radius of the outer ring equal to 5, there would have been only one possible configuration, 1, 2, 3, 4, 5. However, if we go up to 6, we now have 5 configurations. It's not a large number of possible configurations. We can go a whole lot higher, but it turns out that even this basically simplest possible case is enough to illustrate all the principles that we've seen at much larger number of rings. So for each configuration that is possible, and there is 5 of them, we show the radius of the central disk, the inner and outer radius of the first ring, the inner and outer radius of the second ring, the outer ring. We show the actual absolute value of the 6th order truncation term coefficients, because with 2 rings, we can cancel out 2 times 2, 4 truncation terms up to the order of 4, which makes the 6th order truncation terms the smallest remaining truncation term, and its coefficient, its absolute values are presented here. And we also calculate the increase, the percentage of increase in truncation term coefficient with respect to the optimal. So of course, for the optimal, the percentage of increase is 0%. From there on, it goes all the way up to almost 100%. So even with outer ring equal to just 6, from the optimal configuration to the worst case configuration, we are increasing the Laplacian estimation error basically twofold, virtually twofold. So here are the principles that define that optimal configuration and allow you to define it for any number of rings, any size of the electrode. First of all, we notice that in the optimal configuration, the radius of the central disk is minimal. The width of the rings, except for the outer one, is minimal. The distances between the rings is minimal. And then we just put whatever area is left into the outer ring. So that's our number one, the optimal configuration in the table. We also see that larger width of the outer ring is better than the smaller width of the outer ring. If you compare the configurations 1 and 2, you will see that 1 is better with a larger outer ring. You can also see that if you need to increase the width of a concentric ring, it's better to increase that width closer to the outer ring than increasing that width closer to the central disk. Those configurations will fall behind. Increasing the width of any ring is better than increasing the radius of the disk. The only configuration that has a larger radius of the central disk is the absolute worst configuration here in terms of the Laplacian error. And last but not the least, if you really have to increase the distances between the elements, between the recording surfaces from the minimal one, at the very least increase that distances closer to the outer ring as opposed to increasing that distance closer to the central disk. You will do better off increasing those distances closer to the outer ring. Now, again, this is a very oversimplified case, which luckily just allowed us to illustrate all the principles involved. But as we look at a more sophisticated example, you will see that all the same principles hold perfectly. So, for example, in this case, we now have outer radius of the outer ring, or the size of the electrode, the radius of the electrode equal to 9, up from 6. And now we have 70 different possible configurations. And the interesting thing is, why did we go with specifically 9? Because this configuration number 15 and configuration number 30 are configurations B and A from our previous graph. Those linearly increasing entering distances and constant entering distances. Because when we introduced the comparison framework, we introduced it just so happened for the radius of 9. So we decided to recreate that. So our two previously introduced configurations ended up being 15th best and 30th best, respectively. The optimal configuration, this number 1 configuration, is portrayed right here. And again, it adheres to the principles from the previous slide, where the radius of the central disk is kept at 1/9. All the distances between the rings are kept at exactly 1/9, which is the minimum in this case. And the width of the outer ring is kept at the highest value possible. So we compared this optimal configuration, this panel C, to the ones that we considered previously, our constant entering distances B and our linearly increasing entering distances. We've noticed that the Laplacian error, that this perfect, excellent predictor of the Laplacian error, increases twofold going to linearly increasing entering distances. So from C to B, it increases threefold if we go from C to A. Which means this optimal configuration gives you a Laplacian error that is, I'm sorry, the linearly increasing entering distance configuration gives you a Laplacian error that is twice higher than the optimal one, and the constant entering distances configuration gives you a Laplacian estimation error that is 3 times higher than the optimal one. So the increase in Laplacian estimation is fairly significant. What do we conclude based on this? First of all, we can speculate why the optimal design turned out exactly the way it did turn out. And if you want, I will speculate on that and tell you my take on what exactly these results mean. But in most general terms, we can say that in this optimal design, those recording surfaces, and specifically the outer ring, accounts for a very large portion of the area of the electrode itself. And if you add all the recording surfaces together, their mutual area accounts for a very large portion of the surface area of the electrode, which happens to be very different from the actual example of the electrodes that you've seen in the very first slide. And if you look at other concentric ring electrodes, including ones that are commercially available, for example, from CRE Medical Corp in the United States, or I'm drawing a blank on the Italian company that is selling them in Europe. I'll get back to you on this. You will see that these optimal designs are very different from the designs that are currently on the market, with those really thin rings, very small disk, or a larger disk on the contrary, etc. Therefore, we hope that this work will help influence the way the design of the concentric ring electrodes evolves in the future for any number of rings. We can also say that we only had a single criterion in this optimization problem, which was maximizing the Laplacian accuracy, which of course is of primary importance. But if we really want, we can add additional optimization criteria. I'm so sorry. Do I need to wrap this up? This is, I believe, is the last slide. Okay. All right. Another thing that we really need to look into is with concentric ring electrodes, you always have to be wary of recording surfaces not ending up way too close to each other, because at certain points, and the electrodes are usually held in place with conductive paste, an issue of salt bridges may become significant enough to affect the accuracy of Laplacian estimation. So that's with optimal designs really minimizing those distances between recording surfaces. You have to be even more careful of that. We were able to confirm these results with finite element method modeling, not only to show that the actual Laplacian error for those two previously proposed configuration really is 2 and 3 times higher than the Laplacian estimation error for the optimal electrode from this study. But we also did a study on how the depth of the dipole affects the results. Luckily, it doesn't. How the amplitude of the Laplacian estimate changes, because that may influence the signal to noise ratio, etc. So we are hoping to do an extended version of this paper for that special issue in sensors. And that's basically it. Thank you guys so much for your attention, and any comments, questions, anything, be happy to address them.
Thank you so much for the interesting presentation. I don't know if there are any questions from the audience. Yeah, Jael, please switch on the microphone.
Could you kindly illustrate one example where these electrodes are used?
Absolutely. Do you want to choose an organ system? And I'll do an example, or all right, let's say brain. In brain, its applications were mostly related to epilepsy, from the simplest applications like seizure onset detection, which can be, of course, done with regular EEG electrodes. But it was even more successful in locating and detecting really local, really low amplitude signals. Like, for example, we are talking high frequency oscillations, HFOs, which is this signal that appears in the EEG right before the seizure onset, or sometimes an amount of time before the seizure onset, and is virtually undetectable with non-invasive electrodes. So usually it's detected with intracranial single pole electrodes. With concentric ring electrodes using the Laplacian, the second derivative of the potential, instead, we were able to show that we can detect high frequency oscillations preceding seizures in the Laplacian signal, mostly based to elimination of global artifacts, which highlights those local low intensity signals, and also due to better spatial resolution. So that's in terms of brain signals. In terms of heart, let's say, the latest paper we did was Technical University of Valencia last year in sensors, I don't reference it there, showed that with Laplacian signal from concentric ring electrodes, and we used a quadripolar, so 3 rings concentric ring electrode. Actually, I think we went with a tripolar. Yeah, we used the tripolar, linearly increasing and linearly decreasing entering distances tripolar electrode. We showed that we can increase the diagnostic yield of that cardiogram signal for diagnosis of disorders that rely on the contrast of the P wave. So if the contrast of the P wave is beneficial to making a right diagnosis, the Laplacian signal was the one that was producing the best contrast. With other organ systems, I know that the recordings from the uterus are mostly used right now, and it's again Valencia team who is doing this work to detect any kind of disorders or problems related to different stages of pregnancy. I believe that's where their most of their work is.
Many thanks. Thank you.
Of course, absolutely.
Okay.
Yeah. Alberto?
I have a question. I'm interested in the measurement of bioimpedance. Do you think that this kind of electrode can provide an advantage in terms of spatial resolution of the measurement of the bioimpedance with respect to the conventional wet disk?
Thank you, sir. Boy, I know the person who would be the perfect perfect candidate to answer this question in the best way, but I'll do my best. And the person who studied the bioimpedance, the salt bridges, the partial shortening, all of those related issues the most is Dr. Walter Bisaya from the University of Rhode Island. His group have published on it as recently as last year. In terms of impedance, all the experiments that we did on, let's say, animal models in terms of the impedance of the electrode as opposed to a single pole regular gold cup electrodes. With the use of the same thermal paste and the same positioning on, let's say, rat scalp, we did not see any difference in animal model in impedance values. Has it ever been studied through, let's say, analytical, mathematical modeling of the impedance? The first steps towards it have been taken again in 2018. I think it's IEEE Transactions on Biomedical Engineering, Dr. Bisaev's paper in 2019. The first steps were taken there, but the analytical results and, let's say, animal model results have not been tied perfectly just yet. Let's see if I can answer this even better.
No, it's okay. It's okay.
Oh, thank you.
And the last one is about the how you can produce a tripolar concentric electrode. How difficult is to work with materials, or it's quite easy just because they are conductive?
Thank you, sir. That's an excellent question. The fabrication methods actually have evolved quite a lot in the very last decade. Originally, concentric ring electrodes were always printed on rigid substrates, so like saying gold-plated electrode recording surfaces on something like PCB, for example. Lately, the results have been favoring flexible substrates, actually, that adhere to the surface of the scalp or skin better. So it's basically any dielectric polymer and recording surfaces printed on it, either in silver or in any other conductor. So at this point of time, with printing, the cost of the concentric ring electrodes have been decreased quite significantly. There is a way to produce them as disposable electrodes. There is a way to produce them as reusable electrodes. Originally on the rigid substrates they were, and even commercially available, majority of commercially available concentric ring electrodes right now are still on rigid substrates and are multi-use. It is possible to print them on a fabric. That's out of the latest results that I've seen on this. So it's quite possible that the future is actually fabric printed electrodes for single use.
Yeah, interesting. I think also tattoos with electrode inside. Yeah.
Oh, that could be the next step.
Just to delete the problem of some impedance between the skin and the electrode. Okay, thank you so much. Very interesting topic. That's all, Alberto.
That's all. This concludes this session. I would like to thank all the presenters. Thank you again. And I would like also to thank the attendees for to be here with us.
Thank you all for your participation and for your presentations, and have a nice evening, and I wish you a nice weekend.
Okay.
Yes.
Thank
Thank you very much.
Thank you then, everyone. Bye-bye and have a good weekend.
Bye-bye.
Bye.
Bye.
Bye. Bye.